So in this video, let us look at a shortcut to increase the roots by a fixed number. For example, if you have a polynomial a0 x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus so on up to an is equal to 0. If the roots of this equation are alpha 1, alpha 2, so on up to alpha n. Now let us assume that I want an equation whose roots are alpha 1 plus k, alpha 2 plus k, alpha 3 plus k, so on up to alpha n plus k. That means I want an equation whose roots exceed the roots of this equation by a constant k. So we have already seen the substitution that we need to do. So what is the substitution that we need to do? So we take y is equal to x plus k and substitute x with y minus k. So the required equation is, a0 times y minus k power n plus a1 times y minus k whole power n minus 1 plus a2 times y minus k whole power n minus 2 plus so on plus an is equal to 0. Now the problem with this is that we need to expand each of this and collect the corresponding coefficients. So let us say that we have done all of that. So let us say that this is equal to some capital A0 times yn plus capital A1 times y power n minus 1. So let us say that we have collected all the coefficients correspond to y power n and the corresponding coefficient is A0. I have collected all the coefficients correspond to y power n minus 1 and the corresponding coefficient is capital A1 plus a2 times y power n minus 2 plus so on up to an minus 1 into y plus an is equal to 0. So let me write a coefficient just before this an. Now your aim is to find a0, a1, a2, an minus 1 and an. So usually you'll be asked to expand this to find this a0, a1, so on. Let us take an example to see the difficulty here. So if you have an equation of the form x power 5 plus 2x power 4 plus 5x cube minus 4x plus 6 is equal to 0. If you want an equation whose roots are, so if this equation has roots this, if you want an equation whose roots are exceeding the roots of this equation by 2. So what you need to do is you need to put y minus 2 in the place of 5. So y minus 2 power 5 plus 2 times y minus 2 power 4 plus 5 times y minus 2 whole cube minus 4 times y minus 2 plus 6 is equal to 0. So till this point it is easy, but to expand this is not very easy. So you have to expand y minus 2 power 5. So you get y power 5, y power 4, y cube, y square, y at constant term. Here also you get a lot of terms. Here also you get a lot of terms, so on. And you need to collect all those terms. After collection, you might get some number times y power 5 plus some other number times y power 4 plus some other number times y cube plus some number times y square plus some other number times y plus some number is equal to 0. So if you can have a shortcut to derive these numbers, that would be very useful. So now let us see how we can easily derive these numbers using Horner's synthetic division. So now we have understood that we need some process to find these capital A0, A1, A2, so on. So how do we do this? So now what we do is, let us do the back substitution again. Now if I want to convert this equation into the original equation again, if I want to convert this equation into the original equation, what is the substitution that I need to do? So in the original equation, I substituted x is equal to y minus k to get this equation. So in this equation, if you substitute y is equal to x plus k again, you get the original equation, right? So original equation can be found out by putting y is equal to x plus k again. So a0 times x plus k power n plus a1 times x plus k whole power n minus 1 plus a2 times x plus k whole power n minus 2 plus so on plus an minus 1 times x plus k plus a. This is exactly same as the original equation. So this implies the original equation can be written as x plus k times a0 times x plus k whole power n minus 1 plus a1 times x plus k whole power n minus 2 plus so on up to an minus 1 plus a. So the original equation can be written as x plus k times this plus a. So can you see that if I divide the original equation by x plus k, the remainder is nothing but the last number. The remainder is nothing but the last number a. So dividing by x plus k is very easy. To find the remainder is also very easy. Now once you get an, the quotient is nothing but this. The quotient is this. So in the quotient, you get an minus 2 times x plus k again. So if you divide this again by x plus k, now the remainder will be the next coefficient. And you get some quotient. And if you divide it again by x plus k and find the remainder. So successively, if you find the remainders of the quotient by dividing with x plus k, at each stage, you get the numbers starting from the last coefficient to the first coefficient. So this is the process which we do to get this a0, a1, a2, so on up to an minus 1 very easily. So let us apply this process and see the beauty of this process. So as the first example, let us take the same question that we have already solved in the previous section. X cube minus 3x square plus 5x plus 2 is equal to 0 is the equation whose roots are alpha, beta, gamma. And you're asked to find the equation whose roots are alpha plus 2, beta plus 2 and gamma plus 2. So if you want the coefficients of the required equation, you just need to divide this equation by x plus 2 successively and find the remainders in each case. So let us use Horner synthetic division for this. 1 minus 3, 5, 2. You need to divide by x plus 2, right? You need to divide by x plus 2. So we use minus 2 here because we need to change the coefficient of the constant term. You need to change the sign of the constant term. So let us start doing this. So 1 minus 2 is minus 2. Minus 3 minus 2 is minus 5. Minus 5 into minus 2 is 10. So you get 15. 15 into minus 2 is minus 30. Hence, the first remainder is minus 28. The remainder of the first stage is minus 28. That means the last coefficient is minus 28. Now, let us continue this process again. So again, let us divide with minus 2. So 1 into minus 2 is minus 2. Minus 5 minus 2 is minus 7. Minus 7 into minus 2 is plus 14. And the remainder in the next stage is 29. Now let us continue the process. Again, we'll divide with minus 2. So you get 1 here. So 1 into minus 2 is minus 2. The remainder is minus 9. And the last remainder is 1. So now that means the required equation is nothing but 1x cube minus 9x square plus 29x minus 28 is equal to 0. So you can see that this type of process is very simple, but this can be used only for the special case of transformation where you need to add some number to the roots or subtract some number to the roots. So let us take few more examples to demonstrate this process. The more the degree of the equation is, the more easiness this process brings to the solution. In this example, you have a 5th degree equation 2x power 5 minus 6x power 4 plus 5x cube minus 2x square plus 6 is equal to 0. And the roots of this equation are alpha i's, that is alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5. You are asked to find the equation whose roots are alpha I minus 3. That means you are asked to reduce the magnitude of the roots by a constant 3. So how do we get the coefficients correspond to the transformed equation? We just need to divide this successively by x minus 3. So divide original equation successively by x minus 3. So let us use Horner's process again. So 2 minus 6, 5 minus 2, 0, 6. You don't have an x coefficient, you need to write a 0. Now if you want to divide by x minus 3, you need to use plus 3 here, right? So 2 3s are 6, 0, 0 3s are 0, 5 3s are 15, minus 2 plus 15 is 13, 13 3s are 39, 0 plus 39 is 39, 39 into 3 is 90 plus 27, 117. So 117 plus 6 is 123. So that will be the constant term of the required equation. Now again let us go forward. Let us again divide by x minus 3. So you have a 2 here. Let us write a 3 again. So 2 3s are 6. So you get a 6. 6 3s are 18. 18 plus 5 is 23. 23 into 3 is 69. 69 plus 13 is 82. And 82 into 3, 246. So 246 plus 39, okay, 285. We got the next coefficient. Now let us again go forward. Again let us divide by x minus 3. So you get a 2 here. 2 3s are 6. 6 plus 6 is 12. 12 3s are 36. 36 plus 23 is 59. 59 into 3 is 150 plus 27. 177. So 177 plus 82, that is 259. 259. So let us again do the same process. So 2 3s are 6. Get 18 here. 18 3s are 54. 18 3s are 54. You get 100 plus 13, 113. So coming to the final stage, again we divide by 3. Shift 2 here. 2 3s are 6. So 18 plus 6 is 24. So you got all the coefficients starting from the highest coefficient to the lowest coefficient. So the required equation is nothing but 2x power 5 plus 24 x power 4 plus 113 x cube plus 259 x square plus 285 times x plus 123 is equal to 0. So this particular question would have been very cumbersome if we use the standard process. That is, if you directly try to put y plus 3 in the place of x and try to simplify this will be a very big question which is very difficult to simplify. But using Horner's synthetic division, we have very easily solved this question. So if you want to diminish the roots by k, divide by x minus k. If you want to exceed the roots, that is, if you want to make the roots as alpha plus k, you have to divide by x plus k. And when you divide, we know that you need to change the sign of the constant term so that the process instead of subtraction will become addition. So I hope you have understood this easy shortcut. Thank you.